Okay, so once again, for students of batch 2, I'm just repeating this point that the part that we were supposed to cover in the next lecture, which got disrupted by issues with Zoom and all that, we will cover that in the next lecture. Okay, so since we are with batch 1 right now, we will just cover angle is called the angle of the prism. So I'm coming to that. Okay. So for students of batch 2, RTPS batch 2, okay, there is one more thing in between before we come to the prism, which is combination of lenses and combination of lens with mirror. That we'll be discussing in your next lecture. Okay, so now hopefully if you made that diagram, so now you come to these relationships. Just to correlate them with the diagram you made, you'll understand. So ultimately, it's very important for you to memorize these two formulas so that you don't have to do this derivation every time. Rest you will solve by using the equations, and we'll discuss how we'll solve. Okay, so let me just mention here. E is called angle of the prism. Okay, so these two relations are clear. Okay. So now let us see a typical example. Suppose this is 60 degrees, and the light that we have incident over here making an incidence at an angle of 37 degrees, and refractive index is 1.5. Now we want to find angle of deviation. So this becomes a detailed calculation. We will have to use a calculator to find the various signs and all that. Okay, so here given I is equal to 37 degrees, we'll first use the relation sine I is equal to mu sine R1 to calculate R1. So this will give us 0.6 is equal to 1.5 times sine R1. So R1 will come as sine inverse of 6 by 15, so that is 2 by 5 or 0.4. Okay, so if I work that out now, so I'm just using a scientific calculator here to tell you how much the sine inverse is. Okay. So just a second. Yeah, so this is about 23.6 degrees. Okay, this will come about. R1 will come approximately this. Okay. So that means now, so this was our relation 1 that we used. Okay. This. So now let us say we know that beam of light has bended inside something like this, and it's incident there now. So we know that this angle R1 has become that much. Now we can calculate angle R2, because we know that the sum of R1 plus R2 is 60 degrees. So the next thing in the sequence becomes R1 plus R2 is equal to the angle of the prism. That was our third equation, so we are making use of that. So here R2 becomes 60 minus 23.6. So it becomes 36.4. So R2 becomes this. And then we have the relation that mu sine R2 is equal to sine E. That was actually a second relation. So we substitute this here. So from this we will get E as sine inverse of 1.5 into sine 36.4. So sine 36.4 will be very close to sine 37. So we can even use an approximate value. But anyway, I'm using a calculator, so I'm going with that. So that is, yeah, very close to 0.6 actually into 1.5. So that will give me very close to 0.9. So it's about approximately now I'll calculate the sine inverse of that, and that will give me about 62.9 degrees. This is what I'm getting as the angle of emergence. So that's done now. So now once I've got the angle of emergence, I know that the angle of deviation will become I plus E minus A. That was 37 plus 62.9 minus 60. That is approximately 37 plus 2.9. So that is 39.9, or we will say approximately 40 degrees. So this is what the net deviation is in this particular case. Okay. So we now also know that in this ray will come out such that your angle of emergence is what we calculated there, and if we have to produce this ray forward and this ray backward, then this angle, the angle of deviation, is about 40 degrees. What we calculate. Okay, so this is the way you would do a calculation for the deviation given a prism's properties. Okay. So in this, the angle of the prism is given, and the refractive index is given, and the angle of incidence of light on one side is given. So from that we can calculate all the other required quantities. Okay, people. So hope this is clear. Just make a note of this. Right. So I've actually used a Android calculator to calculate the sine inverses and all that. So obviously, in exam situation, either the values will be given to you, the required values, or the data will be such that it sets nicely to some known values. Okay, now the next thing you have to understand here is the principle of reversibility of light, how that applies. So the reversibility principle works out like this, that suppose I have a given prism, has a given angle, etc., refractive index mu. Now I make light incident from this side at a certain angle of incidence, and it comes out from this side at a certain angle of emergence. So this is my angle of incidence, and this is my angle of emergence, and my angle of deviation is therefore, in this case, I plus E minus E. Now, if light were to be incident in exactly the opposite manner over here, okay, so let me just see if this works. So if something like this were to happen now, that instead the incident light was this, and this was the refracted light. So here also the angle of deviation will come out to be the same. Here the angle of incidence is actually equal to E, and the angle of emergence is actually equal to I. But the deviation delta is same as in the first case. Okay. As are also these two angles, R1 and R2. This will remain R2, and this angle will remain R1, same as it was over there. Okay. So that means for a given prism, okay, a given angle of deviation can occur for two angle of incidences. Okay. For example, in our previous example, okay, we had angle of the prism equal to 60 degrees. In one case, we had angle of incidence equal to 37 degrees. So angle of emergence came out to be 62.9 degrees or whatever approximately. Okay. And deviation came out to be 39.9 degrees like this. Okay. But in another case, if we keep the angle of incidence equal to 62.9 degrees, the angle of emergence will come out to be 37 degrees, and the deviation will be the same. This just implies this. Okay. So, and we can even reverse the figure. Okay. So, this told us here that if this angle was 37, then this angle was about 62.9 because this angle was 60. Now you see here there is reversibility applicable. Okay. So that means that if I flip this diagram also, I'll get the same thing. So what I mean by saying that if I flip this diagram is this, that if now the light is incident from this side only, but at an angle of 62.9. It's incident like this. Okay. Then it will emerge out like this. Let's see. So if it is incident like this, but this angle is now changed to 62.9, then this angle of emergence will automatically change to 37, and the deviation will be the same. Okay. So this is what we mean by the reversibility of light. I mean, not just reversing the direction in the given diagram, but if I actually take two separate cases where light is incident from this side, okay, and again light is incident from this side, but in this case the incidence is 37, so the emergence is 62.9. So in this case, if the incidence is 62.9, then the emergence will have to be 37, and the deviation will be same in both the cases. Okay. So just make sure you understand this part over here and make a diagram of it. Okay, people, so hope this is clear. So this also means that if I were to plot, let's say, we were to plot a graph of the angle of deviation with respect to the angle of incidence. So deviation as a function of incidence. Okay. So we would see that for every angle of deviation, okay, this graph would give two particular angle of incidences. For example, here, for that data point of 37, we had got the angle of deviation of about 40 degrees. But we also got for the angle of incidence of about 62.9 or whatever, 63 degrees we got this. Okay. So we'll see that in general, every angle of deviation has two particular angle of incidences. Okay. And this graph follows some particular pattern like this. But there's a particular angle of deviation which happens where there's a unique angle of incidence. Okay. So you can see here, if 37 degrees is the angle of incidence, then 62.9 becomes the angle of incidence. But on the other hand, if angle of incidence is 62.9, then angle of emergence becomes 37. Okay. So for the deviation equal to 40 degrees or whatever, okay, the angle of incidence can be 37 degrees or 62.9 degrees. Okay. Like that. So basically for any delta, okay, I is equal to I1 or I2. Okay. So E is equal to E1 or E2 such that I2 becomes E1 and E2 becomes I1. It's like that. Okay. However, for no, it's not a parabola. It's an undefined curve because it comes from sine inverse function and all that. It's a inverse trigonometric kind of relation. It's a little bit more complex. Okay, in fact, it's not even symmetric. We'll see that this particular angle, say I naught, okay, we'll see is not symmetric between these any two other angles. So for the minimum deviation condition, we'll see that the angle of incidence is a unique angle. Okay. That means whatever the angle of incidence, that becomes the angle of emergence. Okay. So just note down this graph and this part first, then we'll come to the calculation using this. So basically, it's a little bit like using maxima minima theory, along with using the actual graph that you can draw by doing experimentation. Like you can just take some other angle like 30 degrees or 27 degrees or something and show that how the angle of deviation keeps dropping as you go from 37 upwards. But as you go from 37 upwards, your angle of emergence will also keep decreasing because the angle of deviation is decreasing. But there will be a certain point where you reach that angle of incidence and you increase the angle of incidence beyond that, again your deviation starts increasing. That means there is one unique angle at which the deviation is minimum. And now logically you can see, because it's a unique angle, so that means I1 is equal to I2. So if from this figure you can see that if I1 is equal to I2, that means I has to be equal to, because I2 was nothing but E1. So there is a unique angle of incidence, not two values, a single value where the deviation becomes minimum. Okay, so now from this, there is a kind of special relationship that comes for this minimum deviation condition. So let's look at that more carefully. So the condition for minimum deviation is that if delta is equal to delta minimum, then I must be equal to E, which must be equal to I naught. So the moment I is equal to E, that also means that R1 is equal to R2 is equal to E by 2. So this is one very easy way by which we can, okay, so we see that the diagram looks very symmetrical first of all, the ray diagram that is. The symmetry works in such a way that incident this way. For example, if this is an isosceles triangle where this angle is equal to this angle, then this becomes parallel to the base. But this need not be an isosceles triangle. As you can understand, this prism can very well be cut like this also. So it makes no difference at all whether you cut it like this or it's cut it as an isosceles triangle. So more importantly here, what will happen is that you apply the reversibility principle. See that how this works out. Okay. Now, so this angle will be equal to this angle, and this angle will be equal to this angle. And therefore, our angle of deviation we get as this. This angle here is delta minimum. So formula wise, it works out like this, that R1 equal to R2 equal to this. So now sine I naught is equal to mu sine R1, which is E by 2. Okay. So I naught we can say is sine inverse of mu sine E by 2. Okay. And therefore, the minimum deviation will become, so the angle of deviation in general was I plus E minus E. So that becomes 2 I naught minus E. So the minimum deviation angle is now given by this formula. It is 2 times sine inverse mu sine E by 2 minus E. This becomes the formula for the angle of minimum deviation. So of course, we will be doing another version of this when we look at thin prisms, and we can do small angle approximations in that. But on its own, this is an important formula because you understand the minimum deviation condition. So just make a note of this. Okay, so again, let's check out what we are getting for our example which we have taken. In our example, we have taken the angle of the prism to be 60 degrees and refractive index to be 1.5. See what you get for I naught, and accordingly you get for minimum deviation. Okay, so let's see what this is working out to be. So in this particular example, I told you this our angle of incidence will work out to be such that sine I naught is equal to mu sine A by 2. So that is 1.5 into sine 30 degrees. So that will become 3 by 2 into half. So 3 by 4. So I naught will become sine inverse 3 by 4. So let's work that out in a calculator. So 0.75 sine inverse, about 41.4 degrees. Okay. So our minimum deviation will work out to be approximately 82.8 degrees minus 60. So it will work out to be approximately 22.8 degrees. And one angle of incidence is equal to the angle of emergence. Okay. So if we go back to that example graph that we had drawn, you can see here that this will be about 28.8 degrees. This will be about, how much was it? 40 point something. 41.4. So the values here being for that set. Okay. The values are for now the other question is, what about maximum deviation? Okay. What is the maximum deviation that we can have? So hope this is clear to all of you. Okay. Now the other side of the graph is is the maximum deviation we can achieve. So what we mean by this is maximum deviation just before total internal refraction. Yeah, but what was the question? Come again. Some of you are getting a different answer. So the angle of the prism is the angle on top. Okay. So I'll answer your doubt separately. This angle A is called angle of the prism. A is called. No. Maximum deviation is not angle of the prism. Okay, I'll come back to this. And some of you are getting 48.6, is it? Let me check. You mean the minimum deviation? Okay, let me check. But this is okay, na? This formula over here that I've written. Mu sine, sine I naught is equal to mu sine R, which is E by 2. So if the angle of the prism we have taken is 60, is 30, so this will become 3 by 4. So 0.75 sine inverse. Okay, I made some kind of mistake. Wait. Just this correction here. This will be about 48.6. This will be a different value. Sine I naught is equal to 3 by 4 will give us this. So now double of this minus 60 will give us about 37.2. I naught minus E will give us minimum deviation about 37.2 degrees. So the values change slightly. So let's come back here, this graph. So actually you can see that this point is very close to the minimum deviation. That 3762 case is very close to the minimum deviation. But also another thing you can notice here is that this is not a symmetrical graph. 48.6 minus 37 is about less than 9 degrees and is less than 10 degrees, and this one is more than 10 degrees. So it's not a symmetrical graph. So now let us come to the maximum deviation case. Now let us understand first of all what we mean by maximum deviation. So we saw that if you are at an angle of incidence such that you are getting a certain angle of emergence which is greater than your angle of incidence. Okay, so suppose you are at a situation like this, you are getting something like this. So we are at a situation where I is less than E. Okay. Then definitely we can see that I is less than I naught. Okay, because if you think of your graph, it's like this. Okay. So if this is a particular angle of incidence, then for that one the angle of emergence is this one. So if I is equal to I1, then E is equal to I2, and vice versa. So if I is less than E, then you are definitely at the point which is less than your minimum deviation condition. Okay. So now, if you go to I plus delta I, oh sorry, you go to I minus delta I, you go backwards like this to increase the deviation. So if we are at an angle of incidence where this is the case, that the angle of incidence is less than angle of emergence, that means our I is less than the angle at which we'll get the minimum deviation condition. So that means increasing our I will decrease our deviation. So to explore the maximum deviation position, we have to actually go backwards. I1 से पीछे जाना है या I2 से आगे जाना है. Okay. So if we change our angle of incidence to I minus delta I, then our angle of emergence will increase. We'll go from this to this. So if I'm bringing the angle of incidence to less than I1, then the angle of emergence will increase to more than I2. So E prime will increase to E plus some delta E. Okay. And our deviation will increase. And delta increases. Okay. So let's not confuse the delta signs here. Okay. So like this, how much I can increase this emergence before emergence stops happening. Okay, so as we continue to decrease our angle of incidence, what happens is E increases and delta increases till we reach a limiting situation till the limiting value of I, for which delta becomes maximum, but more importantly, what happens, the emergence becomes tending to 90 degrees. So we have what we call grazing emergence. Okay. What I'm saying is यहाँ से अगर मैं angle of incidence कम करूँगा तो angle of deviation, angle of emergence बढ़ेगा. But at a certain angle of emergence or at a certain angle of incidence, what will happen is this kind of thing will happen. Just a moment. So at a certain angle of incidence, this kind of thing will happen. Okay. So this thing will become that limiting case where we have what we call grazing emergence. Okay. Or E is equal to 90 degrees. Okay. So that gives me the maximum deviation. So maximum deviation condition one way is grazing emergence. Okay. So for that E is equal to 90 degrees, the maximum possible value. I will be equal to the minimum possible value. So I less than this, there will be TI, okay, which we'll find, and which also we'll find. Okay. So if our angle of incidence becomes less than this I minimum we are calculating, then there will be total internal reflection. And last two here. So again, your mu sine R2 becomes sine E, which becomes 1. So R2 becomes sine inverse 1 by mu, which is nothing but the critical angle for the glass. So therefore R1 becomes E minus critical angle, and therefore that I, which is equal to the minimum value of I, that becomes sine inverse mu into E minus critical angle. So this value now gives us this position in the graph. So graph will be generally something like this, where this is 90 degrees, this is whatever that I minimum is, correspondingly this is our maximum deviation, and this is our minimum deviation, and this is so condition for delta minimum is that E is equal to I, equal to I naught, R1 equal to R2 equal to E by 2, okay, and that sine I naught is equal to mu sine A by 2, and that minimum deviation becomes 2 I naught minus E. Okay, so this is a simple way to remember how this works. And the condition for maximum deviation, so in that we have case 1 where I is equal to I minimum. So emergence is equal to 90 degrees, which means that R2 is equal to critical angle, which means that R1 is E minus critical angle, okay, which means that I minimum is sine inverse mu into E minus, ये उसका पूरा कंडीशन हो जाता है. So there is also case 2, so I'm coming to that, but you will understand that from reversibility. So first just understand this sequence of events we talked about. Okay, so from the trend of this graph, you can understand that if I am at an angle like I1, which is less than I0, then decreasing the angle of incidence results in increasing the angle of emergence. So how far can I decrease? I can decrease to a point where I just about have emergence. If I decrease further than that, I will not have emergence, and instead what will happen? TIR will happen. Okay, so I don't want to get into a situation where this is what happens. Incidence and then this. I don't want this. I want emergence to come out from here. So the critical condition becomes when emergence is grazing. So to answer your question, mu cannot be less than 1, no? Because speed of light cannot be greater than speed in air or vacuum. But yes, you can have a situation where the prism is put inside a liquid which has a greater refractive index. Then its behavior becomes different completely. So Sudhir has asked a question: what if mu is less than 1? So that is not practically possible. But what you're trying to understand with mu less than 1 is a situation where light bends the other way. As it goes into the prism, it bends away from the normal, and as it comes out, it bends towards the normal. So that will happen if you put the prism inside a liquid which is having greater refractive index. Okay, so hope that is clear with it. Alright, so grazing emergence, once you understand this thing that you're going on decreasing I here till you come to this critical condition where your ray is just about coming out. Any more and it will do TIR over here. Okay? So then you realize that okay, that is the condition where your emergence is becoming 90 degrees. Once you know your emergence is 90 degrees, the rest of the calculation is very easy. So at the second refraction, you can see that यहाँ पे emergent ray ऐसा है, so that means this angle of incidence here, which is what we call R2. Okay, so if E is equal to 90, it means that R2 must be equal to critical angle. And if R2 is critical angle, then you know that R1 must be equal to this E minus critical angle, and then I becomes easy to calculate. Okay. So for example, in that question that we had, where angle of the prism was 60 degrees and mu was equal to 1.5, our critical angle will come out to be sine inverse 2 by 3. So that I'm just telling you how much it is. 0.67 ka sine inverse. So that is about 42 degrees approximately. Okay. So that will tell me that my I minimum will be so 18 degrees, 60 minus 42, okay, into 1.5. That's 24 degrees, sorry, 27 degrees, and sine of something we've written wrong over here. Just a minute. This final formula, there is a sign inside this. Because basically we are using that formula, that sine I is equal to mu sine R1. Okay, so R1 is this. Yeah, so coming back to that, my angle of prism was 60 and critical angle was around 42. So 18 degrees is R1. So sine of R1 is 0.3 approximately, so into 1.5, and then sine inverse of that. So this will come close to about 27.6 degrees. Okay. And the minimum deviation itself, sorry, maximum deviation itself will become this I minimum plus 90 minus angle of the prism. So that in this case, that we is all that is just summarized over here in this. Also in this. Okay, people. So hope this is clear. Now the second case in which we can get maximum deviation is very simple. Okay. Case 2 over here is just where the angle of incidence tends to become 90 degrees. So this is grazing incidence. That's just the reverse of that ray diagram. So in this case, you just apply reversibility to the above ray diagram that we had seen. You will understand how this case works. So suppose we were at some point like this on the graph. Okay. So in order to increase, so our angle of incidence is somewhere here. Let's say. So in order to increase our deviation, we have to increase angle of incidence. So up to where we can increase? We can increase up to the point where we are just having grazing incidence, where the angle of incidence is just tending to 90 degrees. And by reversibility, the moment the angle of incidence tends to 90 degrees, our angle of emergence will be this I minimum which we have calculated. Okay. So that you can see by this kind of ray diagram that light is just about grazing in emergence, in incidence like this, almost parallel to this. So this here will become like the critical angle. This. So here the angle of incidence is tending to 90 degrees. Then for angle of incidence tending to 90 degrees, R1 becomes critical angle. So R2 becomes E minus critical angle, and emergence becomes that sine inverse mu of sine R2. So you substitute this here, you see it becomes that I minimum. Okay. And our deviation becomes maximum deviation. It becomes 90 plus I minimum minus. Okay. So that is the other case of this. So those are the two extreme values. Understand this? That is about the complete analysis of the prism in general. Okay. Okay. Now, another aspect we'll understand is that if you compare a prism with a larger angle compared to a prism with a smaller angle, so if E2 is less than E1, you can see that the graphs will be such that the range of deviation will be different. So this has something like this. This will have comparatively a smaller range. So range of deviation, that is delta max minus delta minimum. Okay. So it will be like this. If this is A2 and this is A1. So you can see that the range is less for, so if A2 is less than A1, then the range of deviation for the second prism is less than for the first prism. So this is an important thing which we now follow into the case of extremely thin prisms also. We'll discuss. So you can just figure that out by taking the value of I minimum that you get for a grazing emergence. Okay. That angle A figures in such a way that you'll realize that that range between I minimum and 90, that decreases as your angle of the prism decreases. So automatically your range between delta maximum and delta minimum also decreases as the angle of the prism is decreasing. So from this we'll understand that as you come to thinner and thinner prisms, you come to that region where you have an extremely thin prism, where the angle of the prism is less than about 5 degrees. So you can start using small angle approximations. Okay? So this becomes an important set of formulae which come from approximations. So thin prisms, where the angle of the prism A is less than about 5 degrees. Therefore, sine A becomes approximately E, but of course in radians, not A in degrees, but A in radians. Okay. So for thin prisms, what happens is that we have that formula. So first of all, for thin prisms, the range of deviation is extremely short. So that means any delta is approximately equal to the minimum deviation. Okay. And so basically what we are saying is that for any incident ray, if an emergence is happening, then that emergence is happening at a very short range of deviation. So because it's a very short range of deviation, we can approximate this delta as approximately the minimum deviation. Okay. And for minimum deviation, so any delta is approximately equal to, and condition for minimum deviation is that I is equal to A, R1 equal to R2 equal to E by 2. Okay. So here sine I naught is equal to mu sine E by 2. Okay. Now in this figure, since A is a small angle, therefore sine A by 2 will be approximately equal to E by 2. Okay. Therefore I naught, which is sine inverse of mu sine E by 2 will become equal to sine inverse, approximately equal to sine inverse of mu into A by 2. Okay, because sine A by 2 can be approximated as E by 2. And then this itself is a small angle. Okay. And mu A by 2 itself is a small angle. Therefore, sine inverse of mu A by 2 is approximately mu A by 2. It's the same thing as saying that sine theta is approximately theta, implies that theta is approximately sine inverse theta. The same thing. So I naught is approximately mu A by 2. Okay. So therefore now my minimum deviation thing, which was 2 times I naught minus E, becomes approximately mu minus 1 into E. And finally, since the range of deviation is very small, that means maximum minus minimum deviation it's tending to 0. Therefore, any general deviation is approximately mu minus 1 into angle of prism. So this is deviation by a thin prism. Okay, and in the final formula, since we've taken angle on both sides, we can take this in degrees also. Though in all the approximations is taken in radians, but in the final case, you're relating a small angle with another small angle. So you can convert both from radians to degrees. So you can get the angle of deviation in degrees as mu minus 1 into the angle of the prism in degrees. So I'll just take you through this step by step and make sure you understand all the steps in between. Yeah. All right. So hope this is clear. So for example, if you have the angle of the prism as 3 degrees and the refractive index as 1.5, then the angle of deviation by such a prism will approximately become 1.5 minus 1 into 3, or approximately 1.5 degrees. So every time there's a ray of light incident on it, it will almost pass through undeviated. Very small angle of deviation. So another way to understand why the deviation is very less for a thin prism is to understand it like this, that suppose that a thin slab. So what happens to a ray of light incident over here? It's undeviated. It just has lateral deviation. It does not have any angular deviation. It just comes out like this, parallel to this. So delta equal to 0. But now if you have in comparison a prism but something which is, so these two sides are nearly parallel to each other. So accordingly, the deviation will be very less. Oops, sorry. Very minute amount of deviation. Here delta. So that's the logic of understanding why there is very minimal deviation. Okay. Right. So that is all about prisms. So that actually completes everything that we need to know for JEE advanced type of problems. Okay. Of course, for RTPS batch 2, we will be coming back to combination of lenses and combination of lens with mirror in the next lecture. But now we come to a portion which is specific for JEE mains, which is optical instruments. So in HC Verma, there is a specific chapter only, but you can just treat it as a section of geometrical optics. But this is only for JEE mains. So the concepts are actually a continuation of concepts of lenses and all. So that way it is nothing new, but the formula that the specific formula that we'll derive and all that, those formula are for direct application only in JEE mains syllabus. Okay. So before we get into optical instruments, we will understand the concept of angular size of an object. And from that, the concept of angular magnification. What that means, let's understand. So if we have an object like this, and this is the eye of an observer, then the object subtends a certain angle, and that is called the angular size of that object. So theta is called as seen by this observer. Now you can see in this diagram that if I bring the same object closer, its size is not changed, but it will appear magnified. Why? Because the angular size is increased. If I took it further away, its size is not changed, but it will appear smaller. So that's why angular size plays a very important role in our understanding of size of an object and depth perception. Okay. If we had only a single eye and our vision was not, from the comparison of the images coming to the two eyes, so it did not have any depth perception. If our vision did not have depth perception, then we would never be able to tell the size difference because of distance or angular size. So, all those type of photographs you see where people try to create the illusion that something further away is smaller than them, even though it is much larger. That happens because two-dimensional photographs don't have that depth perception. Okay. Same reason why, if an observer is looking at a very distant object, so if this is where your eye is, okay, and there is one object A over here moving with a certain velocity VA, and much further away, yes, Suti, good point, yes. Zero movie was, yeah, partly made by this concept. Okay. Now suppose VB is greater than VA. Okay. Like this is, let's say, an aeroplane very far away. And this is like a bird much closer. Okay. So VB is definitely greater than VA. But after some time, B has, let's say, reached over here. And A has reached over here. Now see, the angle covered by A is more than the angle covered by B. So delta theta for A and delta theta for B are different. So, but delta theta for A appears to be greater than delta theta for B. So A appears faster than B. Okay, so this is another implication of this whole concept of angular displacement and angular. So our vision is also based on the angular size, and therefore our perception of movement is also based on the angular motion of objects around us. Okay. So in optical instruments, this is the problem we are trying to circumvent. Okay. So for a small size object, for example, if you're looking at print on a paper, the size of alphabets, etc. So that print could be an alphabet or a number or something like that. Okay. So it's a very small size object in that sense, compared to the distance at which you are keeping it from the eye. So this is where your eye lens is. So that height of the object is very small compared to the distance at which you are keeping it. Then the angular size, which is becomes approximately equal to h by x. So tan theta. So we're using theta is approximately tan theta. Okay. So now the important thing is that for the vision of that particular object to be well focused on your retina, your eye lens has a limitation, and that limitation is that it cannot focus objects which are closer than something called the least distance of distinct vision. Okay. So the maximum angular size that you can get without any optical instrument in between is when you bring this object closest possible to your eye, such that still you are able to focus on it. So that closest distance is called least distance of distinct vision. Okay. So now the human eye has a limitation, and that limitation is that it cannot form a well focused image for x less than capital D, where capital D is called the least distance of distinct vision. Anybody knows what the value this is? The average value? Just a minute, people. I'll have to reload my whiteboard software. Just hang on for a second. So while I'm doing that, yeah, that's correct, Ashwin. About 25 centimeters is the least distance of distinct vision. Just a moment, I'll have to reload that software because it's starting to give. So the value of capital D, Ganesh, correct, is about 25 centimeters. Yeah, actually it varies from person to person because obviously it's biologically everybody is different, okay, but average statistically over population is. So coming back to this, just a moment. So coming back to this, the maximum angular size for a small object, that we denote with a special notification, which is theta naught, is h by capital D. This is for unaided view. That is when we are not using any optical instrument. So now using an optical instrument, if we are able to increase the angular size to theta, then that theta related to this theta naught is called the angular magnification using that optical instrument. So first of all, we have understood the concept of angular size. We have understood the concept of maximum angular size to the unaided eye. Now next thing we'll understand is angular magnification. So suppose our object is kept at the capital D, which is least distance of distinct vision. Okay. So for brevity, this is also called near point of the eye. So the angular size of the object you just see is h by capital D. But suppose we keep some optical instrument in between, and as a result of that, what we are seeing is a different version of the object. We are seeing the image. So this is the image we are seeing. So that image is subtending a larger angle for us, theta, and theta is greater than theta naught. So then the angular magnification is denoted by this symbol m theta. That becomes theta with the instrument divided by the maximum theta without any instrument. So here, this is called the angular magnification. Okay, where theta is the angular size as seen through the instrument. But remember, what we are seeing through the instrument is of the image. We're not seeing the object directly. We're seeing some kind of an image of the object. Okay. So that image's angular size, we are getting the illusion of seeing that image. So that has an angular size which is greater than the maximum angular size that we can see without any aid of instrument. So that ratio is called the angular magnification. So the purpose of any optical instrument, starting from the simplest of ones, which are your hand lens or magnifying glass, to complicated compound microscopes with multiple lenses and all that, the purpose of these type of optical instruments is just to increase the angular size of an object. Of course, electron microscopes and all work on different principle, and that is more complicated using quantum mechanics and all that. But here we are talking about optical instruments. So we are still talking about manipulation of light in terms of refraction and reflection, without any of the quantum effects coming into picture. In fact, without diffraction and interference also coming, only through reflection and refraction. Okay. So now let's see the type of optical instruments. So the first one is simple magnifying glass, or what you can call hand lens, or what some people glorify by calling it simple microscope. But it's not really something that complicated. Okay. It's just a simple hand lens. So that is basically just a convex lens of focal length f. So what happens is, suppose this one. So let me try and draw this in perspective. Okay, so suppose this is something like this. Okay, so you can see the comparative theta naught is h by d. Looks small enough in my diagram also, but imagine it's, this h is much smaller and d is a bit larger, about 25 centimeters. Okay. Now suppose between my eye and that object, now I've kept a lens, okay, such that that object is now kept somewhere between the focal point of the lens and the pole. Okay. So you know that the rays of light here will deviate in such a way that will give you an image somewhere here. If this object was H, it will show, okay, a magnified upright virtual image. Okay. But more importantly, this image that you're getting at the eye, it is having an angular size. Now ignore the distance between the eye and the lens. So it's having an angular size which is this theta, the same as this theta. That is the angular size. So the angular magnification we have achieved is this theta divided by our earlier theta naught, where theta naught was just h by d. Okay. So now, if our object was kept at a distance x and the image is formed at a distance y, we also have the relation that you can see theta is equal to h by x, which is equal to h prime by y, where you have 1 by v minus 1 by u is equal to 1 by f, or this kind of relation also. So now coming back to this, angular magnification is becoming theta upon theta naught, which if we write in terms of h so that it cancels out, so it is d by x. Okay. So if the focal length is such that for a given x which is less than capital D, y is greater than capital D, okay, then our eye is able to create a focused image. Okay. Because remember what the eye is seeing is the image, okay, which is at y from the pole. The eye is not seeing the object anymore. So the fact that the object is closer than the least distance doesn't matter. As long as the image that the eye is seeing is greater than the near point, okay, so we'll be able to create a focused image. Okay. And we'll be able to achieve an angular magnification, which is d by x. Okay. Now we'll see different cases for this and the range of magnification that we can achieve using a given lens. We'll understand that also. But first, make sure you understand the concept of angular magnification itself. Right. So people hope this is clear. Yeah, sorry. Scroll down. Okay. So this becomes the angular magnification. Okay. Now you can see that if we put x nearly equal to the focal length, then y will tend to infinity, or basically very large distance. So in this case, what happens is, because it's a the image that we are seeing is at a very large distance, it is a very comfortable situation for the eye. So that is why this is called therefore, x equal to focal length is called the normal adjustment position. Okay, for the lens. So when we keep the object at a distance which is equal to the focal length, we achieve an angular magnification of d by f. And this is called the normal adjustment position. So what happens at normal adjustment position is that the magnification is the minimum possible. We'll see we can get more than this, okay. But the eye is comfortable because the image that we are seeing is comparatively very far. Okay. So this is what we call the normal adjustment position. Now, very opposite to this is, now if x becomes less than the focal length, okay, that is the object is between the virtual focal point and pole, okay, the image comes closer to the pole, okay, from infinity. Okay. Now the thing is, as the image, so y also becomes finite now, okay, because x is less than f. Okay. So now, as x is decreased, y also decreases, but y should not be less than capital D, because capital D is the near point of the eye. Okay. So minimum value of y for clear vision is capital D. So therefore, minimum value of x is that value for which y is equal to capital D. Okay. So we'd seen earlier that 1 upon d minus 1 upon u was equal to 1 upon f. So solving this, we had got x is equal to dy upon d plus y. Oh, sorry, fy upon f. So in this equation, substitute this concept. So we get the x minimum. df upon d plus f. And now, angular magnification, which was d by x, becomes this. become 1 plus. So this position is called the near field adjustment. Okay. That is when the image is at the eye's near point. Okay. So this corresponds to the maximum angular magnification possible. But also it corresponds to maximum strain on the eye. So in general, what will happen is your X should be between focal length and that X minimum, and correspondingly angular magnification will be in this case. This is for X equal to X minimum and Y equal to capital D, and this is for X equal to focal length, Y becoming very large. So this is the normal adjustment position, and this is the near field adjustment position. So actually, if you just understand this concept only properly, then the rest of the type of optical instruments like compound microscope, etc., become very easy to understand, because they achieve the same thing but using a combination of lenses. So this is what we had seen earlier. First, we'll go through the normal adjustment position concept. Okay. So this is the case where my magnification is minimum possible, but the eye has maximum comfort because your image is at a very large distance. And on the other hand, if we now make X less than the focal length, then the image also comes closer. But so this relation is inverse of this actually. Y should be greater than equal to. So the minimum possible value of Y should be capital D. We should not bring the image closer than capital D, because then our eye cannot focus and view it properly. Okay. So the corresponding value of X for which Y becomes capital D, that is my X minimum in my range of X. So that X minimum comes out to be this way. And for that particular adjustment where my X is X minimum, so that my Y is becoming capital D, the magnification comes out to be this much, the angular magnification. So this is the minimum to maximum magnification that you can achieve for a given. So now based on this, you have compound microscope. Which is really the same thing but achieved through two lenses. So compound microscope has a combination of two lenses. One called the objective lens, typically we denote the focal length as f(o), and the other is called the eyepiece with a focal length of fe, because we keep the eye right against this. The eye is placed right against this, and the objective lens actually looks into the object. The height of the object is h. Again, if we keep this at a distance x1, let's say over here. Now x1 happens to be greater than the focal length of the objective. So the objective actually creates a real image of this. Somewhere over here, let's say. Let's say this is h1. So this is the real inverted magnified image by the objective lens. Now this one actually becomes also the object for the eyepiece. That is that h prime or that h1. And if the distance of this here is y1, now this distance is, let's say, x. So again, we adjust the distance between the lenses such that x is less than focal length of the eyepiece. So the eyepiece creates a virtual upright and magnified image of h1, which I'm showing in the next diagram. Okay, so just create the distinction here with a different color. Okay, so now this one produces an image, let's say somewhere. So this is the image as finally seen by the eye. Because x is less than the focal length of the eyepiece, so it will create an image which is further behind, and like this. So the final angular size that the eye is seeing is this theta. So if this h2 now, this final image by the eyepiece, if this is at a distance of y from this pole, this distance is y. So it creates an image such that 1 upon minus y minus 1 upon minus x is 1 upon f of the eyepiece. And earlier for the objective, we had the formula that 1 upon plus y1 minus 1 upon minus x1 was equal to 1 upon f1. And we had that h1 by h was linear magnification, which was nothing but y1 by x1. I mean, there's a minus sign involved, but I'm just taking mod. So this is the magnification due to the objective lens. This, of course, is linear magnification. So we have this. So again, that tells us that x is equal to f into y divided by y plus that kind of. Again, if you go back to that above diagram, you'll see that the angular size of the final image seen by the eye, that angular size is basically h2 by y, which is the same thing as h1 by x. Let's go back to the diagram and understand that. Okay, so your eye is finally seeing this, and its angular size is going to be this theta, which is the same as the angular size of the object in terms of x. So h2 by y is the same thing as h1 by x. So basically, the relationship between this h1 and h2 here with respect to the eyepiece is the same as the relationship between the object and the lens in the case of a single hand lens or a simple hand lens. So our angular magnification will be this angular size divided by the reference size for no instrument. So it will be h1 by x divided by h by capital D. Now, h1 is the linear magnification produced by the objective into h. So you can see that this becomes m into d by x. So the angular magnification is even more compared to a hand lens. For a hand lens, it was d by x, but now it is multiplied by a magnification factor m, where m is the linear magnification by the objective lens. Okay. Now, once again, for x equal to the focal length of the eyepiece, y tends to infinity or very large. So this is called the normal adjustment position. So in the normal adjustment position, the magnification becomes this much, where x is focal length of the eyepiece. Whereas for near point adjustment or near field adjustment, y should be at its minimum value of capital D. So the final image, because of height h2, is at the eyes near point. That kind of situation. Okay, so for that to happen, y is equal to d means x is equal to this. Okay, because that was a relation between x and y. So our angular magnification will become m into d by x. So that becomes m into 1 plus d by x. So again, you can see the formula is symmetrical. For simple hand lengths, it was 1 plus d by f and d by f for normal adjustment. Here it is d by fe and that's multiplied by a factor of the magnification. So this is the maximum angular magnification. And the image is at near point. So there's maximum strain for the. Okay, so this is the concept of microscope. I'll just take you through the ray diagram once so that you understand this. Okay, people, so hope this is clear. Okay, so from this we get this as the general formula of angular magnification. It is linear magnification produced by the objective into d by x, where x is the distance of the object for the eyepiece, which is actually the image for the objective. X is the object distance for the eyepiece. It is also actually the image of objective with respect to whole of eyepiece. So now we can adjust the value of x such that the final image y is anywhere between the near point of the eye to infinity. So when it is at infinity, it's called the normal adjustment position, and when it is at capital D, it is called the near field adjustment. So correspondingly, we get this kind of range of magnification. Okay. So our final angular magnification ranges between this and so that is the understanding of compound microscope. So hope this is clear, people, and we will conclude our session here today. Okay. So next lecture for group 1 students will be a sort of wind up lecture. We will discuss about terrestrial and astronomical telescope, which is a very simple application of this, but I don't want to confuse too many things today. So let's keep it up to microscope because the concept of telescope is slightly different. So we'll keep that for next day, but it's just a few minutes. And then a section called dispersion of light. where we'll see how a prism splits white light into its component colors and the related chromatic effects of that. So again, that will take a few minutes, but apart from that, most of the lecture will be about problems, discussion, and especially if you have any doubts and things we'll discuss. Or otherwise, we'll do some good IIT level problems from before. Whereas for group 2 students, of course, the next lecture will be about combination of lens with mirror. And that's again going to be very important lecture from JEE Advanced point of view. Because those type of questions are specific for JEE Advanced. Combination of lens and mirror will rarely come in JEE Mains level questions. It is more about JEE Advanced type of questions. And then the final lecture after that, we will come back to dispersion and analysis. Okay. So that's it for today, people. I will send you the whiteboard notes as well as the yes. I will send the whiteboard notes as well as the recording. So you can revise everything from there. Now also try to complete everything from HC Verma and from your booklet for the lenses and combination of lens type of problems. And in HC Verma, there's a separate chapter on optical instrument. It starts with the explanation of the human eye itself, including all the biological terms and all that. So you can go through that just for general knowledge, but it's not really required for JEE. And you can concentrate on the part which starts with the microscope and telescope, those kind of things. Okay. All right, people. So that's it. All the best. Okay, and stay safe.